Okay, today we'll work on chapter 6. Um, the first important point I want to state about chapter 6 is there are 3 homework assignments. We will cover the introductory concept and one example problem today. The first homework basically has 2 questions. The first is a short answer question about concepts, and the second one is a problem, which would be very, very similar to what I do in class today. Second point is we will have a quiz, one final quiz next week based on chapter 6. But I will not assess chapter 6 on the final exam separately. Okay. So the total assessments for chapter 6 will be these 3 homework assignments and the quiz next week. And that's it. Then you're done. All right. So those are the 2 points about chapter 6. Okay. So let's see what it is about. It is one of my favorite topics. Well, I say that about every chapter. Okay. Frequency response. Yes. It's there. So from the Canvas front page, and it's been there since the first day of class. Let's see. There you go. So again, final exam from the front page. Oh. And there was a question being asked in the Zoom chat also. So I guess they should answer questions for everyone. The final exam link on there. And then there are 4 options for students. Again, final exam is mandatory in the sense that if you do not take it, I mean, you don't have to take it if you don't want the grade. That's all. I mean, if you're happy with your grade as it stands before the final, you can leave with it. But again, final constitutes about 20% of your overall grade. So if you are at 100% so far and you don't take the final, you end up with an 80% in the class, which is like just about a B, right? So if you're happy with that and you don't want to take the final, that's fine. But it's mandatory in the sense that it is part of your grade. There is no skipping that grade. There is no Zoom option. All final exams are in person. There will be rules in place, meaning ID cards will be checked for each and every student before and after you take the final. Meaning, in order to receive the blank final exam copy, you'll need to show your ID, sign the form, and then before you submit, again, you show the ID, you sign, and then you exit the exam room. I will have those rules on here. They are not up here yet, but what is up here is the 4 options that you can take the final at. There's a Saturday final and the university schedule times. And then if you keep going down, the topics are listed. I will remove chapter 6 from here. And then there's also a survey that will allow me to better prepare for the final. Depends on who's taking the final when. So again, you have 4 options. You can take the exam at your university scheduled day and time, which for you is Wednesday, March 20th from 10 to 1 in this room. Okay, 10 to 1 in this room. If you're taking it any of the other times, again, it's in this room. You have the option of taking it Wednesday morning, 7 o'clock, or Friday at 10 o'clock. Oh, it's not PM, it's AM. I'm not going to be here at night at 10 o'clock. So Wednesday, and Friday, or if you wish to take it on Saturday, you have the option to take it on Saturday before the finals week. A lot of my students do like to take that option so they can get done with 201 and then get it out of the way and focus on their major classes for the finals week. Okay, let's get back to question being asked. We will have only 4 questions of the final exam. I don't know yet because I haven't set the final yet, but I do know is the first question will test chapters 1 and 2. It will run 1, 2, 3, 4 pages long. So do you need to specify which final session you will attend beforehand? Yes, you do need to specify, especially if you do wish to take the final on a Saturday, you do need to specify which day you wish to take. So there is a form at the end of this page. Go ahead and fill out their form. Several students have already filled it out. Actually, several students filled it out in the first week itself. So I do know that a lot of you are taking the final on a Saturday. Okay, I'm going to stop right there because the page lists all the information that you would need. So read through it and then email me your questions. Okay. All right, let's go back to where is OneNote? There we go. All right. What does this remind you of? I heard washing machine as an answer in the first section. You're college students. If this doesn't look familiar, then you need to get out more. Okay. Engineers are known for working hard, studying hard, and partying hard. Okay? This is a rough illustration or a crude illustration of a speaker box. It's a speaker box. Now, admittedly, my drawing skills are not up to par, but still. This is a three-way speaker box, meaning there are three different speaker drivers or three different speakers inside this box. What is this one called? The big one. It's not quite a subwoofer, but yes, it is a woofer. Subwoofers are different because of the frequencies that they reproduce. They need to be large and to be powered separately. So a good subwoofer is a separate box, which, well, is a whole different system. Anyone have a subwoofer in their car, by the way? Any buddies? Anybody? You have one? Yeah. I had two in my car, but not, I did the work myself. Picked up a couple of speaker boxes from Walmart, amplifier from Radio Shack when they were still around, and wired it up myself in an old beat up junk of a car. But I used to rock it, so it was good. This, well, what the answer? What is the small one? Tweeter. And this one is for mid-range. Woofer reproduces low frequencies. The loud thumping bass sounds that you hear in the music or in movies, right? Vocals, mid-range are vocals. So hence the mid-range of frequencies. And tweeter reproduces the high frequencies. Okay, high frequencies. The reason for the size disparity is the lower you go in frequency, the more physical space you need to reproduce the sound, because the wavelength is inversely proportional. Okay, so depending on the wavelength of the frequencies, well, actually, let's not get into the physics. Let me come back to the main point. So this the speaker box has three different drivers. Yet, if you look at the back of the speaker box, you'd have a connector with only two terminals, meaning only one wire or one cable is going in there. That one cable will have, of course, two wires, one for positive, one for negative. Yet it is connected to three different speakers, right? And each one of these speakers has two wires or two connections. So what is the purpose of having three different speakers, and how is that one cable being split into three? Because I just said, right? Woofer reproduces low frequencies, the tweeter reproduces high frequencies, and the mid-range produces mid-range frequencies, the vocals. So what is happening is, if you open up the back of this connector, it's easy to do. There are just a couple of screws, and you remove it out, you'll see that when the two wires go in, it goes to a circuit box. And there's a circuit inside. That circuit, depending on how expensive this box is, the design and the build quality and the components being used, will have several inductors, resistors, and some big capacitors. And it will have 3 outputs or 3 pairs of outputs. This one might be going to the woofer, this one might be going to the tweeter, and this one might be going to the mid-range, depending on the configuration. Not saying that the inductor output is going, I'm just saying there are 3 pairs of outputs, and each one is actually going. So it's splitting the incoming signal into 3 ways. Hence, it is known as a 3-way speaker or a 3-way speaker box. Most speakers are 2-way speakers, just the woofer and the tweeter. Especially like car audio systems, it's just a 2-way speaker system. Home audio, it's 2-way speaker system. Okay. What the circuit is doing, it is filtering out certain signals based on the value of the incoming frequencies. Okay, so all of the frequency signals are coming from your amplifier or your receiver, and it's going into the speaker box. The first thing it encounters is this circuit. And the circuit is known as a crossover network. Crossover network or a crossover circuit. And technically, it is an electronic filter. Or an electrical filter. And as the name suggests, a filter filters out unwanted signals. Okay, unwanted signals. And so you could take a wire, not a wire, take an incoming signal, connect it to this circuit, and it filters out, basically, if it's going to the mid-range, it's going to filter out the low frequency signals and the high frequency signals. It's only going to allow a certain frequencies that is in the middle to pass through. Low frequency signals, by the way, are the ones that are about 50 hertz for this particular circuit, about 50 hertz frequency to about 200 hertz. Actually, not 200, that's I'm talking about the subwoofer. Low frequency signals here would be about 50 hertz to, let's say, 500 hertz. It seems like a large number to us, right? 50 times in 1 second or 500 times in 1 second, but they're considered to be low frequency. High frequency signals are in the kilohertz range. Okay. So anyway, this circuit utilizes the frequency dependency of an inductor and a capacitor. Okay. The frequency dependency of the impedance of an inductor and a capacitor is what allows us to actually do this filtering magic. And hence the name of the chapter, frequency response. Okay. We learned in chapter 5 that the reactance and thus the impedance of an inductor and capacitor changes with respect to frequency. ZL is J2 pi FL, meaning the impedance of an inductor increases when you increase the frequency. At high frequencies, an inductor behaves like an open circuit. Okay, remember, chapter 3, DC, constant voltage, inductor behaves like a short circuit. So frequency F is equal to 0 or very low, inductor behaves like a short circuit. When it increases, the impedance increases. ZC is inversely proportional. It's 1 over 2 pi FC. It's 1 over F. So as frequency increases, capacitor becomes a short circuit or behaves like a short circuit. When the frequency is lower, capacitor blocks out those frequency signals. There's high opposition. And so that is the magic that allows the filter to work. Well, it's not actual magic, of course. Anyway, some of the most common frequencies are listed here. But again, as a practical example, electrical signals in wired circuits as well as in wireless circuits all work due to the magic of filters. If you take wireless signals, for example, or for instance, there are wireless signals all around us. A human body is a receptor for all wireless signals in the air. Okay, we are bombarded with FM radio signals AM radio signals, television signals, satellite, mobile, cordless signals, Wi-Fi, Bluetooth. We have signals, wireless signals all around us. So how do we prevent the interference from one kind of signal with another one? And that's where the filters come in, right? If you ever buy a phone, not just a smartphone, any kind of wireless cell phone from a particular company, there are three major ones in the US: T-Mobile, Verizon, and AT&T, right? And the first thing you would read about is that it's locked to that network. So locked to the network, what does it mean? It's an electronic device. If you use a global version of a smartphone, it's unlocked. You can buy unlocked phones in the US also. You can use it on any network. The reason is because each wireless operator broadcasts their signal, meaning sends their signal in the air at a particular frequency. And that frequency is a range of frequencies that is controlled by the government of each country. And the government of each country has a regulatory authority. In the US, it's the FCC and the FTC. Okay, FCC and FTC. Actually, no, FTC is Trade Commission. FCC is the Communications Committee, I think. So FCC is the one that handles the spectrum, and they auction it off. Okay, so the companies bid at an auction to purchase this frequency spectrum for a certain period of time. It's very expensive, very, very expensive, and very, very valuable. And whichever company buys it has the right to broadcast only that frequency. No other company can broadcast it. And that's how they lock your signals. That's how they lock your smartphones. Okay. If the smartphone cannot access that frequency, it's not going to work. And there are many other ways of blocking it, but this is the first, this is the first step. So if you buy a global version, which by the way, my phone is a global version, it can work anywhere in the world because it has frequency bands that are compatible with, well, most frequencies around the world. Even your phones that you buy here in the US are also globally compatible. If you buy an unlocked phone, or if you buy a locked phone and you get them to unlock it, you can use it anywhere in the world. Okay, and the reason is it is accessible to all range of frequencies. And the way they can ensure that the signals from AT&T do not interfere with T-Mobile, or Verizon signals do not interfere with AT&T, is by having a filter at the front end of the device. That filter will only allow a certain frequency to enter, and everything else will be blocked out. Okay, that's one of the ways of implementing, well, filtering out signals. AM radio signals. AM stands for amplitude modulation. FM stands for frequency modulation. We are not going to study those in this class, of course. But you have ever hear of the term 680 AM, 680 AM, or 101.7 FM? That number is actually technically derived from the actual broadcasting frequency of that radio station. So 680 AM, you would actually tune your radio to 680 kilohertz. AM radio stations broadcast in the kilohertz range, FM in the megahertz range. So 101.7 or 101, 99.6 FM is basically the broadcasting frequency of the radio station. It's broadcasting at 101.7 megahertz, which that is actually a high frequency, right? But now we work in gigahertz and terahertz range also. So the clock cycles for a CPU, we say a processor, Intel Core i7 processor running at 4 gigahertz frequency. It's a clock cycle. There's a clock inside every chip that keeps it synchronized, keeps everything synchronized. So that's a very high frequency, 10⁻⁶, 10⁻⁹, 10⁻12, very high frequency signals. Anyway, so we have all these frequency signals, whether in wired circuits or wireless circuits. The thing that keeps unwanted signals out is a filter. Okay, that's an electronic filter, and that is what we're going to study in this class. In this chapter. So far in circuit analysis, we are used to applying a voltage or a current from the left side of the circuit in an illustration. And then you have a resistor, and perhaps you have multiple components in the circuit. And that's it, right? We are used to analyzing. You don't have to draw this diagram. This is just for explanation purposes. And then we would analyze a circuit to determine the voltages and currents through various components. In this chapter, we're going to think and approach a little bit differently. Now, a voltage source or a current source has two terminals. Okay, two terminals. We will group those terminals together and we call it a port. And so if you group these terminals together, we have one port. It's known as a port. Okay. And any place where you take a output or you measure an output, again, we'd group it together and we'll call it a port. And so a circuit can be split into input and output. And we'll put the actual circuit with the components inside a sealed box. Okay, it's a sealed box. And we don't know what is inside the box, and we don't really care. At least for the first portion of this chapter. And then, of course, here we have the output port. So the sealed box, again, at this point, we don't know what's inside the box. We don't really care. We only need to know what that box does. Okay. So this box is, of course, a circuit or a network. And we say that it has two ports, an input port and an output port. Okay. So an input port comprises of two terminals. Output port also comprises of two terminals. So it's known as a two-port, two-terminal network. Two-port, two-terminal network. It's a two-port filter network. And what it is doing is, it is basically amplifying or enlarging certain frequency signals, and it is diminishing or attenuating certain other frequency signals depending on its function. So as an example, what it is doing here is you have a large input signal with multiple components, and it's going into a filter circuit. It is breaking it up into different parts, not literally, but again, this is just for explanation purposes. Yeah, Vn1 and Vn2. Vn1 is being enlarged and Vn2 is being diminished. So Vn1 increases, Vn2 decreases. So Vout1 is larger and Vout2 is smaller. And then it combines both together at the output, both together in the circuit, and sends it to the output. Okay. So a filter network accepts the incoming signal. Those incoming signals can be from multiple different sources, depending on the requirements and the design of that filter circuit. It will increase certain frequency signals. It will decrease or diminish certain other frequency signals, add it together and send it to the output. Okay. So again, a sealed box, we don't know what it is doing. We don't really care. It is simply described by a term known as H of F. H of F. Again, sealed box. A sealed box that has a descriptor H of F. And what it is doing is it is simply describing how the input signal is being transferred to the output. And so it is a ratio of the output voltage to the input voltage. V out or V in. And if you look at it carefully, it is the phasor for V out and the phasor for V in. And so H of F is a complex quantity. It has magnitude and it has phase. It doesn't have any units because it's a ratio of voltages. I invented this and named it after me, actually. How many of you did really believe that? No one. No, it's not. Apparently, it's not named for anybody. Some theories are out there which state that it was simply the next letter in line after, E, F, G. And so E, F, G were already being used, and so they decided to use H. There are other theories out there which says that it was named after a German physicist. Can't remember if the name, but I don't even know if it's true or not. Okay. Anyway, it's H of F. It's a unitless number. It simply describes how the input is being transferred to the output. So using the audio system as an example, if the sealed box was an amplifier, we don't care what is inside the amplifier. We don't need to do an analysis. We don't know how it works. We only need to know that the transfer function of that amplifier is a gain of 2. If we know H of F has a value of 2, we know how it's being transferred to the output because it's a ratio of the output to the input, right? V out over V in is equal to 2. We can predict or calculate what the V out would be no matter what the input voltage is. Make sense, right? If H of F is 2 and input is 1, what is the output? Simple math. V out is H of F times V in. If H of F is 2 and V in is 1, what is V out? 2. That's it. V in could be 100 or 100,000, and we'd be able to predict or calculate the output voltage. And that is the point of a transfer function. Transfer function of a sealed box or a sealed circuit network is basically describing how the input is being transferred to the output. And that's it. So let's look at an example where H of F is described graphically. On the left here, it describes the magnitude at different frequencies. On the right here, it describes the phase at different frequencies. We are asked to find V out of t, if the input, the homework problem, by the way, is exactly similar to this one, okay? It shouldn't take you more than 10 minutes to get it done. All right, so V out of t is asked for an input signal of 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t minus 70. Okay. Take a few seconds and look at the input signal. How many components do you see? Anyone? There is these two, absolutely. But this is also a component. It's not quite obvious at first glance. This is basically a constant. It's a DC voltage along with the AC component. And again, we have those also, right? You have, if you plug in, let's see, what example? All right, if you're in a vehicle, sometimes if the line filtering is not good, you might hear the engine whirring noise coming out through the speakers. You may not have personally experienced this. I have, but you may have actually read about it, perhaps. That's the DC signal from the engine and the battery that's coming in through the speakers and interfering with the audio system. So there are filters in place to block out those components. Okay. And so this could be something like that. There is a DC component in the signal. And building off of that, the first thing we'd want to do is, if we want to find how the circuit Again, the circuit is not given to us. We don't really care what it is. We only have been given the h of f function in those two graphs. Okay. So what we would do is we would equate this. We would break this up into three different components. I will call it V in 1 of t, which is 3 volts, and extract the frequency information from there. And then V in 2, and then V in 3. Okay. And then V in 3. This is cos of 4000 pi t minus 70. And what you do is you equate each one of these with a standard expression, right? Vp or Vm cos of omega t plus or minus theta. So here I have Vm as 3 volts, but my frequency f is 0 hertz. That frequency f is 0 hertz. Omega is 2 pi f. The reason I want the value for f is because the charts are given as a function of frequency f in hertz. Make sense? Right? If it was given in omega, I would just take the omega and just work off that. But since the charts are given in f, I need the frequency information in hertz in f. And so here the frequency information is 1000 hertz. F is equal to omega divided by 2 pi. That's why I like these examples. Use a nice round figure. And this is F is equal to, or F1, F2, and F3, 2000 hertz. Okay, 2000 hertz. Once we have identified these three frequencies, we can, the next step is to identify or write down the transfer function at each one of these three frequencies, and then the phasors of these three input component voltages. So the phasor for V in 1 would simply be 3 volts. V in 2 would be 2 with an angle of 0 degrees. And V in 3 would be 1 with an angle of minus 70 degrees. Those are the three phasors for the three input voltages. Okay, let's go over the chart and write out the transfer function at each one of these frequencies. H of 0, 0 is right here. Is 4. And the phase angle is, of course, 0. H of 1000 is magnitude of 3 and a phase of 30 degrees. And then H of 2000 has a magnitude of 2 with a phase angle of 60 degrees. Take a 10-second pause, write it down, think over it. Let me know if you have any questions. Does it make sense so far? You have a graphical representation of the transfer function of a circuit. Circuit's not given to us. It's not been described to us. We don't really care what it is. But we can look at the incoming input signal, and we can write out the transfer function at any given frequency based on those graphs, based on the charts. Okay. The incoming signal has three components. Each one of those components has a frequency. We extract the information. We find the frequency is 0, 1000, and 2000 hertz. Then we take those three frequencies, go to the figures, and then write down the transfer function directly, the magnitude as well as the phase. Now all that's left is to apply the equations to each one of these inputs. So V out 1 is H of 0 times V in 1. That would simply be 4 times 3, 12 volts. It's being increased by a factor of 4. V out 2 would be H of 1000 times V in 2. So this would be, let's see, 3 angle 30 multiplied by 2 angle 0 gives me magnitude 6, phase angle 30, and phasor for V out 3 would be H of 2000 times V in 3. Two with a phase angle of -10. And that's it. As easy as that. Again, it's a ratio of the phasor voltages of the output to the input. And so if we know the transfer function, then we can calculate the output no matter what the input is. And that's the point. If you look at the circuit, I mean, even if you just look at the graph, we know that it is amplifying the signal by a factor of 4 at 0 hertz. You look at the magnitude of H of F. And then it's steadily decreasing, 1000, 2000, at least until 2500, it is above 1, right? It is above 1. So it's not interfering with the incoming input signal that is given to us. But if there was a component with a frequency 2500 hertz or above, it would be attenuated to 0. Because there is nothing after that, right? H of F, if F is 2500 or greater, is equal to 0. So no matter what the input voltage would be, if F is more than 2500, the output would always be 0. And it's filtering out all frequency components higher than 2500. Okay. One final step, and then we are done, which is writing out V out of T. And so this would be 12 plus 6 cos of 2000 pi t. Remember, the frequency doesn't change. That remains the same. Plus 2 cos of 4000 pi t minus 10 degrees. And then volts. And that's it. That's the final answer. All right, we'll end class here today. If you have any questions, I'm here. We have time before the next section. Reach out to me over email. But again, I will remind you that homework has only 2 questions. The first one is based on concepts, and the second one is exactly the same as the example I did in class. So if you have some time before your next class begins or before work begins, it'll take you less than 30 minutes. Not even 30 minutes, less than 15 minutes to get that homework done. So while this is still fresh in your brains, go ahead and get it done. All right, I will see you all on Wednesday. So minus 70, question being asked, is minus 70 is given to us in the input. Okay, it's given in the input. Yes.